Hi everyone, and welcome to this quick lecture on the rule of 72. This is like a rule of thumb that people use whenever they talk about doubling time for, say, investments. What we're going to need to derive the rule of 72 is the formula for interest compounded in times per year. We're not going to derive that formula, that's a well-known formula, but the context is, suppose you have some principal amount that you put into a bank. You have an interest rate, so slowly your money is going to grow over time. Now, ideally, you would want your interest compounded as frequently as possible. If it was continuously compounded, then the growth of your money would follow exponential growth like what we've seen with bacteria populations. However, what actually happens is that your money is only compounded at discrete moments. It could be every day, in which case it would be compounded 365 times per year. Or it could be compounded weekly. In that case, n would be 52. Or it could be, say, once a month. In that case, n would be 12. Okay, so we're going to work with that formula. And what we're going to ask ourselves is, how long would it take some amount of principal to double? We'll have an exact measurement for that, and then we'll kind of do some rounding, some estimating, approximating with the natural log function in order to derive this famous rule of 72. Okay, first recall that when we were looking at exponential growth, which you could also think as growth where the compounded interest is compounded continuously, then the doubling time for a population, I called it t star, it's natural log of 2 divided by r, where here r is expressed as a decimal. So if we have an interest rate or a growth rate of 1.2%, then we would write r as 0.012. What we're going to do now is find this doubling time when our interest is not being compounded continuously, but rather discretely. Okay, so what we have here is our formula. So P naught is like our principal that we put in the bank. That's our initial deposit. It's going to be compounded n times per year. So like monthly would be 12, as we mentioned before. The growth rate is r, and then t is time in years. So to make quick sense of that exponent, it's number of times per year times the number of years. So that would be like the total number of times that it gets compounded over the interval that you're looking at. Okay, let's find the doubling time. Just like we already observed with bacteria growth, the initial investment doesn't matter because on the right-hand side, we have P naught like a parameter, and on the left-hand side, I'm going to put in 2 P naught because the idea is we're wondering when our money has doubled. So we'll say 2 P naught equals P naught times this expression, 1 plus r divided by n, all raised to the n times t power. So just like we saw before, we can cancel out the principal amount, so that actually doesn't matter. And just like before, let me call the doubling time t star. So it's at moment t star that we would have this 2 P naught on the left-hand side. Okay, let me just rewrite this now. So we have 2 equals the whole expression in parentheses, 1 plus r over n, all raised to the n times the doubling time. We're solving for that doubling time, so we need to solve for something that's inside of an exponent currently. In order to do that, we take the natural log of both sides so that we can take that exponent and kind of bring it down in front. So we'll have natural log of 2. That's an expression we've seen before. And on the right-hand side, let me go ahead and write natural log of, I'm going to do something a little bit funny here. Since we have n times t star, I'm going to use law of exponents to write 1 plus r divided by n to the n, and then all of that to the t star, and then that's what we're taking the natural log of. That's because when you raise something to a power, then to another power, it's really just going to be the product of those two powers, so we would have n times t star. So the whole reason I did this, on paper I probably wouldn't write this step out, is I'm only going to pull the t star down in front. So I'm going to leave the rest of that exponent inside the natural log and write t star natural log of 1 plus r divided by n all to the n, like that. So basically I separated the n and the t star. Okay, so now we can solve for the doubling time, and what we'll have here is an exact calculation. So we can say t star is going to be natural log of 2 divided by natural log of 1 plus r divided by n all to the nth power. This has some similarities to the doubling time that we saw for the bacteria population. We have natural log of 2 in the numerator, but we have a much more complicated denominator. So while this is an exact measurement, let's do some estimation to come up with like a rule of thumb that we can use for quick mental calculations or to give other people who might not be familiar with the natural log function like a fast formula that they can use. What we're ultimately going to do is first take this 1 plus r over n to the nth power and we're going to simplify it. To do that, we're going to use binomial expansion. So we'll think of this as something plus something raised to an integer power, like x plus y squared. It's essentially the same type of operation happening in here. So we'll simplify that, and then we'll talk about how to simplify that when we plug it into the natural log function. Okay, we'd like to reduce that denominator to something simpler. So first, let's talk about the 1 plus r over n to the nth power. And again, in order to expand that, we can just use binomial expansion. So you might have seen this phrase differently, but what it is if you have something like x plus y to the nth power, where this is something like squared, cubed, some nice integer power, you can expand it according to this binomial formula. This first coefficient here is read n choose k, and here's how you would compute it. So n choose k is n factorial divided by k factorial times n minus k factorial. But what I typically do is I'll just start writing down the numerator, k number of terms, I'll show you what I mean in a second, and then I'll do k factorial. Okay, so what am I talking about? If I have something like 5 choose 3, you could write 5 factorial divided by 3 factorial times 2 factorial. That's the first formula I've given you. Or you can say 5 times 4 times 3. So that's like 5 factorial, but only the first 3 terms, divided by 3 factorial. So 3 times 2 times 1. Okay, so overall that would be what? 10? The 3's cancel out? Yeah, 10. So if I wrote out, say, the entire binomial expansion for x plus y to the nth, instead of using the sum expression up here, you could write it out like this. And if I did something like x plus y cubed, what you would have is n choose 0 is actually 1. So that would be 1x cubed y to the 0. So that's just really x cubed. Plus 3 choose 1 is 3. So then it would be 3x squared y to the 1. Plus 3 choose 2 is also 3. So that's 3xy squared. And then plus n choose n is always 1. So 3 choose 3 is 1. X to the 0 y cubed. Let me put a 1 in there. And you might recognize the numbers 1, 3, 3, 1. Those coefficients actually can all be found in Pascal's triangle. Okay, so if you're ever in a time crunch and you absolutely must compute x plus y to the 7th, then it might be faster to actually write out the first 7 or 8 rows of Pascal's triangle, take the correct row, and then use those coefficients. I'm not sure when you would ever be pressed to do that so quickly, but now you're ready for it. Okay, so let's see what the binomial expansion for 1 plus r over n to the n looks like. Keep in mind here that n is an integer. It's number of times per year. So it could be 365, it could be 12, it could be 52. R divided by n is some decimal divided by n. So that's just some small number. Okay, according to the formula that we just looked at, we can think of 1 as what we were calling x, and we can think of r over n as what we were calling y. So the first term would be 1 times 1 to the n times r divided by n to the 0. So that's like 1 times 1 to the n times r over n to the 0. Overall, that's actually just a really fancy way of writing 1. Okay, the second binomial coefficient is n choose 1. That's actually always n. And then we would have 1 to the n minus 1, of course that's just going to be 1, times r over n to the 1, plus n choose 2. That can be a little bit fancier. 1 to the n minus 2. Of course, that's also just 1. R squared divided by n squared. Then I don't know how many terms I'm going to have. If n is 365, it's going to be a lot. So let me just go to the end. Then we would have n choose n minus 1, 1 to the 1, r to the n minus 1 over n to the n minus 1. That's the form of the next to last term, and then the very last term would be n choose n, 1 to the 0, r to the n over n to the n. Okay, let me simplify this a little bit. As we said, the first term is really just 1. The second term is going to be n times 1 times r over n. So notice that cancels, regardless of what n actually is. So it's 1 plus r. Plus, now you could try to write out n times n minus 1 divided by 2. That's what n choose 2 is, but let me just leave it as n choose 2. R squared over n squared plus, and then I'll skip to the end, r to the n over n to the n, because the last binomial coefficient is 1. Okay, this is an exact expression, but we're approximating here. So what we need to realize is that if r is small, like 7% would mean r is 0.07, then r squared, r cubed, r to the n, r to the 365, those would all be small numbers. So the weightiest part of this binomial expansion, the terms that we kind of feel count the most, are the first two. So overall, this binomial expansion is approximately 1 plus r. Okay, let's remind ourselves what we're even trying to do. We have this complicated denominator down here that might be hard to remember and hard to put into practice, and not everyone even knows how to do natural log and exponentiation and things like that. So what we're saying now is natural log of 1 plus r over n to the n is, given that r is pretty small, approximately natural log of 1 plus r. So that's our first approximation. But we can actually take this further. If r is small, natural log of 1 plus r is approximately r. So if anyone ever stops you on the street and says, quick, I need to know natural log of 1.1, you could say, well, that's like natural log of 1 plus 0.1, that's approximately 0.1. So there's another useful life skill. You can check this, so you can just test it, do natural log of 1.07. Let me actually compute that. I'm wondering what it really is. So natural log of 1.07, in my calculator, the first few digits is 0.0677. So you can see that's approximately 0.07. If you would like to justify this approximation, you could use Taylor expansion. You could use the Taylor expansion for natural log, but that one's a little bit harder to remember. I like to use the Taylor expansion for e to the x. The Taylor expansion for e to the x is 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and on and on. Now let me plug in r, keeping in mind that r is very small. So then e to the r would be 1 plus r squared divided by 2 plus r cubed divided by 6. And just like we did a second ago, we're only going to keep the first two terms, because if r is really small, r squared divided by 2 and r cubed divided by 6 are also very small. The rest of the terms are very small. So we can say that this is approximately 1 plus r. Now you can just take the natural log of both sides. And you find that natural log of e to the r is r, and now we're saying that's approximately natural log of 1 plus r. Obviously, this approximation only works if r is really small. So natural log of 1.5 would be like r equals 0.5. That's 0.4, that's not too bad. But then what about natural log of 3? That would be like having an r value of 2. But natural log of 1 plus 2, or natural log of 3, is 1.09. That's not very close to 2. So this approximation is valid when r is really small, so that 1 plus r is really close to 1. Okay, so what have we done? We've taken this expression 1 plus r over n to the n and said, well, if r is small, because we're looking at a rate expressed as a decimal, that's approximately natural log of 1 plus r. But now natural log of 1 plus r, again, because r is small, is approximately just r. So we end up with the same doubling time that we saw before when we had continuous growth, bacteria growth. Natural log of 2 divided by r. For the exponential growth model, that was exactly the doubling time. Here it's an approximation. So this is already much simpler than what we started with. But again, I want to give you like a rule of thumb that you can tell a child whom you're teaching about investment to, or you can just quickly mentally work with it without having to think about natural log of 2. Here's the rule that we have. Natural log of 2 is approximately 0.69. So where we had t star is approximately natural log of 2 divided by r. We're now going to approximate that a little bit more and say the numerator is like 0.69 divided by r. But keep in mind that r was the decimal version of a percentage. Right? So if someone says interest rate is 12%, r would be 0.12. So let's take the top and bottom and multiply both by 100 to slide that decimal over twice. And this is actually really nice because 100r is just the percentage form. So again, if our rate is 12%, r is 0.12, but 100r is 12. So these are actually pretty nice numbers to work with. Okay, so here's a quick example. Suppose you're investing $25,000 at a rate of 23%, which by the way would be a fantastic rate. So that's not very realistic. Now suppose that this is being compounded 12 times per year. So that would be like n equals 12 in our formula. About how many years will it take for your money to double? Now we could use the complicated formula at the top. So I could do natural log of 2 divided by natural log of 1 plus 0.23 divided by 12, all of that raised to the 12th power. Or I can say that the doubling time, t star, is approximately 69 divided by 23, which is 3 years. How good of an approximation was this? Pretty good. If you use that formula at the top, you would get approximately 3.04 years. So if you're just trying to make a decision on your investment, 3 years versus 3.04 years probably isn't going to be too big of a deal, so this is a good approximation. Now I said this interest rate was not very realistic, but I chose it because 23 divides perfectly into 69. In fact, only 3 and 23 have that property. So in practice, we often use 72 in the numerator because so many numbers divide into 72. You have 2, 3, 4, 6, 8, 9, etc. A lot of numbers divide into 72, which can lead to faster mental math. So 72 divided by 100r, or in other words, 72 divided by the percentage form of your rate, is what we call the rule of 72. Okay, so here's a second example. Had the word example there twice. Suppose this time your investment of $25,000 is invested with a rate of 8% compounded twice per year. How many years will it take your money to double? If we wanted to do this quickly, we would say that's going to happen in about 72 divided by 8 years, which is 9 years. How good of an approximation is this? Pretty good. The true value is closer to 8.84 years. So I'll leave you with a question for you to think about. If you were told the rate is more like 5% or 10%, what would you do?